Okay, so first I would like to thank the organizer for giving me this opportunity to talk in this wonderful conference. So I'm happy to report some recent work which is not published yet, but in preparation. So it's about color kinematic duality applying at a 5-loop level. So this is the plan of my talk. So first I would like to give you some introduction to the background and the motivation. Then after that, I will tell you what is color kinematic duality. And then I will show this how to construct explicitly this 5-loop observable. And finally, there's a conclusion and some outlooks. Okay, so as a background, so as you already heard from the previous talks, there have been tremendous progress in scattering amplitudes in past years. So, and in particular, in the large N limit, namely the planar limit, even a strong coupling or non-predictive results have been obtained, not only for amplitudes, but also for example, the correlation functions that you heard from this morning's talk. This is mostly because of the powerful ADCFT correspondence as well as integrability. So as also emphasized in the previous talk, so much less is understood at non-planar in the non-planar sector. For example, we have QCD, which is has a color group SU3, which is very small in C, and also for gravity theory. For this series, the non-planar contribution is always important, sometimes even dominate the final contribution. So a major challenge is to understand this, the non-planar sector, namely we need to go beyond the planar limit. So the method that we will use in this talk is the so-called color kinematics duality. I will explain to you later in more details. So basically, this feature of this duality is that it contains the color factor. So you know, it intrinsically includes the planar and non-planar contribution. They put them on the same footing. So as long as you know the planar parts, you get immediately all the full parts, including non-planar parts, almost for free. So and besides, it's the method based on this duality also provides an extremely efficient way to construct the complete integrand, and usually in a very compact form. In this talk, we will focus on the integrand. So for evaluating integrals, Johannes Hahn have given impressive talk. So I refer you to those discussions. So I think maybe as people who are not working on amplitudes, you might wondering why Feynman diagrams is not enough, right? Everyone I think here have learned quantum field theory. We know how to write down Feynman diagrams based on Feynman rules. So you just write down all Feynman diagrams that give you the integrand, right? So actually, this works in principle, but the complexity of the expression grows extremely fast when the number of external legs or the number of the loops increase. As already in Song's talk, he shows this tree-level expansion when you increase the number of legs. If you consider loops, it increases also even faster. So one major idea behind this recent developments is to try to avoid Feynman diagrams. This included recursion relations, unitarity Descartes methods, this twistor string formulation, Grassmannian and unshelled diagrams, also bootstraps, and CHI formulation, etc. So here I want to emphasize one particular nice, this method is based on so-called unitarity. This is actually back to the 1960s, where the S-matrix program is popular at that time, before the Lagrangian of the formalism is developed for such as for non-abelian gauge theory. So S matrix is a Lorentz invariant analytical function of momentum variables with only those singularities required by unitarity. So the singularities here means that the poles or branch cards, these are really your physical information, that is the physical input. And the S matrix should be uniquely determined given these singularities. This is the essence of the unitarity. And in practice, this provides a very efficient method to construct the loop integrand. For example, this is a 5-point two-loop example. You can, in this case, you can put 3 internal propagators to be on shell, namely as a delta function. So this two-loop 5-point amplitude is factorized into 2 parts, right? So one is a 5-point tree, another is 6-point tree because these internal legs are on shell. So you can compare with your final results by putting internal propagator to be on shell and compare with these 2 product trees. So if they match, that means that it satisfies this the unitarity at this channel. So a result is guaranteed to be physical, to be correct, if it match with all possible unitarity cards. So this is just the one possible cards. You can perform other different cards. So, so after introducing this background, so the goal of this talk, we will try to test color calorimetric dualities at 5 loop. Why 5 loop is interesting, I will tell you more later. And in particular, we will construct explicitly a 5 loop pseudo-conform factor in X4 CPR mules. And it's combined together, this color calorimetric duality together with unitarity checks. Okay, so what is color kinematic duality? So of course, from the name, you know there is a color part. So this is related to the color factor. We know for Feynman diagrams, there is the trivalent vertex is associated to a structure constant. And there's always a numerical kinematical factors, which is related to the minus time variables. So it's a duality related to these 2 different quantities. More precisely, this conjecture says that for a given amplitude or other observables, there should be a trivalent graph representation. Namely, your graph is always written in terms of this 3-point vertex. And then there is the kinematical numerator associated to this graph satisfy equations that is the same as the Jacobi identity of the color factors. So this is a more concrete definition of this duality. Maybe it's still not so clear. Let's look at a very simple example. The 4-point tree amplitudes. It's the most basic example, but plays a very fundamental role. So just from the Feynman diagrams, we know there is 4 diagrams: this S channel, T channel, U channel, plus this 4-point interaction vertex, right? So you can always rewrite these diagrams in terms of 3. That you, for this 4-point vertex, you can introduce extra propagator by inserting a new numerator. That this can be put in terms of these 3 trivalent graphs, STU channel. Okay. So given these 3 trivalent graphs, you can write down the a corresponding expression. So this STU is corresponding to the propagators, right? So you have a 2 trivalent vertex. So each trivalent vertex give a structure constant FAB, A1, A2, and B here, right? It's a product of 2F. So this F color factor and propagator are determined just by the graph, by topology. So the physical information is contained really in this numerator, right? So so this you can introduce a different notation, CS, CT, CU. So, and we know that the color factor satisfies a Jacobi identity, which is a trivial identity. And this duality tells you that given this relation from color factors, the should satisfy the same relation. So this is give you a non-trivial constraint for your really physical information. So this is I hope this this simple example shows you what's really this color chimeric duality means. So at loop level, this duality is much more remarkable in some sense. Okay, so consider this, for example, the for loop diagrams. So a for loop for-point amplitudes is given by sum over all trivalent graphs. And this graph can be written in terms of this for loop integrals. So of course, there's propagators determined by topology, color factor also determined by topology. The physical information is also contained in this kinematical numerator, right? So this color factor is just product of structure constant. Numerator is a polynomial of these minus time variables. So at loop level, this is still a conjecture. It tells you that for every color factor, for every relation for color factors, it should satisfy another numerator relations. So as you can see, for each internal propagator, you can generate a color factor relation. So this gives you a very strong constraint on the numerators. So how to understand this relation? Actually, if you in a very special case, special limit, you can understand this relation naively just by pick up one internal propagator, and if you cut this adjacent 4 propagators, you just got a 4-point amplitudes, 3 amplitudes, right? So so this 4-point 3 amplitudes of course has its T channel and U channel partners. So in this case, you know that 4-point 3 amplitudes already have a color chimeric duality representation. It guarantees when you do these cuts, the representation can also satisfy this duality. The non-trivial point in this duality conjecture is that the relation should also true even if you lift these propagators to be totally off-shell, that without doing any cuts. So this is the one non-trivial point when you consider loop level. Although this is not be a focus of this talk, I just mentioned this is a very important application of this color chimeric duality, that once you know the Yang-Mills representation that satisfy the color chimeric dualities, you can generate gravity amplitudes totally for free. That's namely just to replace this color factor by another set of numerators. So this is of course, this is going back to the KLT relation that gravity amplitude can be given as a Yang-Mills square. And this BCJ relation is kind of a new kind of interpretation. Also in the Song-Hee's talk, he mentioned the CHY formalism can also prove this relation at tree level. So of course, the remarkable point is that it's also, lots of examples show that it's also true at loop level. So there have been lots of work on this. It's actually the way how people construct the for loop N8 supergravity amplitudes. I would like to mention there are also interesting works that generalize this picture to classical solutions and also black holes in terms of the Yang-Mills solutions. So we will not talk more about this in this talk. Okay. So there have been successful constructions for color chimeric dualities up to for loop so far. So it's for for loop, 4-point amplitudes, it's given in 2010, and in 2012, with collaborators, we also construct the for loop Sudacom form factors. So however, no 5-loop solution had ever been constructed yet. So actually, some people are in doubt whether the duality would work in beyond the for loop. So in this talk, I will show you in the following a concrete 5-loop solution that this duality indeed works. So the example that we will consider is this Sudacom form factor in XOR super Yang-Mills. It's a diagram like this. So you're probably familiar with amplitudes, and in case you are not familiar with so-called form factors, you can just think about as scattering amplitudes involve 3 particles. One is massive, the other 2 is massless. Actually, for the form factor that we consider in INGS4 is exactly the QCD version for this Higgs to 2 gluon scattering amplitudes. So it's also a very important observable that you can keep in mind. So how do we use color-chromatic duality in practice? The general strategy is that we first need ansatz. This ansatz is where the color-chromatic duality plays its role. So general ansatz, which is only depends linearly on a set of parameters. This we will show later with a concrete example. Then, given this ansatz, we need to fix this symmetry, fix these parameters via symmetries or very simple calls. This usually fix a large number of the parameters, and next there one need to nail down whether this solution is physical. Then you need to check against the general integral calls, which would be much more non-trivial. The basic picture is that this very complete Hall loop computation, if you work with Feynman diagrams, it will be extremely complicated and even not doable with a superpower computer. But here, it's basically just a linear algebra problem. So it's very efficient. And let's look at the first, the starting point is to generate the full set of trivertent graphs. That is, you can make ansatz based on this. So for INGS4 super Yang-Mills, there's the extra criterion that one can impose. There's no one loop, bubble, or triangle subgraphs. This is related to the no triangle principle of the INGS4 super Yang-Mills because it's a maximum supersymmetric theory. It's also associated with UV finite property. So for example, this kind of diagrams is dropped out. I would like to mention here, for the form factor, if this subtriangle is attached to an off-shell leg associated to operator, you should keep it. So that's a new feature compared to amplitudes. And in total, there are 370 trivertent graphs to consider. Okay, so just give you an idea how the number of these graphs grows. So we can compare with these 4-point amplitudes and this Sudakon form factor. So at one loop, there's only have 1, 2 loop have 2, 3 loop, there's 12 and 6, 4 loop have less than 100, and 5 loop, you see for 4-point amplitude about 1,000, and these have around almost 400, right? So basically, when increasing one loop, you have a 1 magnitude order increasing. And the complexity between amplitudes and Sudakon form factor is just a factor of 2 also. So it's at a similar level. So next, we need to apply this color-chromatic duality, right? As I showed you before, you can pick up internal propagator and then do this STU transformation. So given one graph, so this is S channel, you can generate a T channel, then a U channel, a 2 new different graph. Because of their color factor satisfy this Jacobi identity, then this gives the constraint on the 3 different numerators. So each propagator will give you such a relation. For each topology, you have 12. So you have 370 topologies. So in total, you have around 4,000 such relations. So this is a huge set of relations between different graphs and their numerators. The constraint is extremely strong. So, and then, because there's such a lot of relations that different topology relate to each other, you find that actually, just given these 4 numerators of these 4 planar topologies, you can generate all other 366 topologies, the numerators. So this is plays the role of the master graphs. So we need to only try to focus on these 4 numerators. So we need to make ansatz for the numerators, right? So of course, for the INGS4 super Yang-Mills, you can have extra this constraint. So first, this is the dimension of the numerators is 6 powers of momentum. I should mention there you factorize a tree factor times this S1 to the square. So you got the 6-dimensional numerator. And then there's related to this no triangle principle. So you have an n-gun sub-1 loop, this diagram. The dependence of this numerator should only depend on this n-4 powers of the loop momentum. For example, you have a box, n-4 is 0, so it shouldn't depend on this L. And you have a pentagon, it only should be linear. So, and also for form factor, there is a small modification, is that if it's associated to this external legs, so it's n-3 powers. So this gives you the answers. Okay. So let's look at the one example of this master integral. So you see there's 4 box, right? So all this loop momentum should be independent of this for loop momentum. But this L, it's 1, 2, 3, 4, 5, 6. So it's associated to this off-shell leg, so it should depend on L only at most cubic order. So now you write down all possible monomials that have in total 6 power of momentum and only depends on L to the 3rd order. So in total, you have 13 terms. So this gives you the answers for this numerator. Okay. So of course, you can do similarly for the other 3 masters. In total, you find there are 162 parameters. So at this moment, you might be afraid that it's such a huge parameter, such a huge number of parameters. It's really hard if you solve linear systems that your matrix is more than 100 dimension. However, so there are lots of constraints that you can impose further. First is this symmetries. Okay, so look at this graph. It's a symmetric, and so the requirement is that the numerator should be invariant under this symmetry, that you just mirror symmetry along this horizontal axis, right? So if you change the loop momentum according to this symmetry, the numerator should not change. So these symmetries for all trivalent graphs immediately fix 115 parameters. So and next, you do some very simple cards. For example, you just perform maximum cards for your master integrals. This fix further 27 parameters. And then you check again whether all Jacobi relations are satisfied. They fix 10 more parameters. So all this procedure might be technical. You can just have a feeling how this works. And it's very straightforward. And so now we only left with 10 parameters. Okay. So next, we should check whether the solution is physical. Right? Now we go to more non-trivial checks. So all this rather non-trivial unitary cards has been checked, and we find they all satisfied, and there's only 3 parameters left. Okay. So just look at this, the most complicated, this sextuple card, because 6 propagator is factorized into 6.3 form factor times 8 amplitudes. So you need to compare with this product tree expression with your answers. Right? The answers is a card of these trivalent graphs. So have a feeling of this tree. You need to compute these expressions. It's complicated, but it's very straightforward to using. For me, I use the MHV rules, and it's very efficient to do it numerically. And then you compare with the answers. So you find that around 100 trivalent graph is involved in this single cards. And there are, for each one, have different card diagrams, about 2,000. So they perfectly match with each other. So these two looks very complex expressions come from very different origins. One is your physical constraints from tree amplitudes. The other is your answers. So it's very non-trivial that they exactly match with each other. So now we come to the conclusion. So we have provide a concrete example that Calumet duality works at 5 loop. So as kind of byproduct, we compute this 5 loop pseudo-conform form factor, which is important physical observable by itself. And I would like to mention actually from this 5 loop pseudo-conform form factor, it contains information of, for example, 3 loop 5-point amplitudes, 2 loop 6-point amplitudes, and also form factor with 3 loop, 3-point or 4-point 2 loop. And you generate this data all in with a color chemical duality satisfied form, which are, I think, not published yet. Of course, these are just a byproduct of this expression. So more interesting questions are, is there other 5-loop examples? So it has been known that 4-point 5-loop amplitudes have some subtleties. So it will be interesting to understand, if not work, why. And pseudocom form factor at 6 loops looks might be also doable. And there is is there interpretation for double copy of form factors? And finally, I think all this the computation you can just do in a laptop, and the most non-trivial expression is just to generate all BC relations. It takes up a couple of hours. All other calculations just a couple of minutes. So it's so efficient with such a 5 loops, so complete observables. Then I think people can ask, why does color chimeric duality work at all, which is still open question. So with this question, I would like to end this talk. Thank you very much.
Yeah, I have a philosophical question.
Yeah.
So, as you know, in the planar theory, there's so much more symmetries. There's Youngian symmetry, and then pessimists are always saying, well, in the non-planar sector, this is all lost, so integrability is lost. We're not going to be able to do anything. But then, if I remember, for 4-particle amplitude at 3 loops, there was this idea that you could choose a master graph, and then using BCJ duality, so you choose a planar master graph, and then using BCJ, all the non-planar topologies followed. But then, if I remember correctly, at 4 loops, I think Johansson told me that now they also had to choose a non-planar master graph. So I was surprised that you had a slide where your master graphs were planar master graphs, and then all the non-planar ones followed.
Yeah.
But somehow, wouldn't that also imply that for the 4-loop 4-point?
Yeah, thanks for asking. Actually, the point is that there's no unique choice for your master integral. So here, I choose 4 master integral to be all planar. So actually you can choose you can reduce the number to be 3. Then you need to introduce 1 non-planar topology as a master integral.
But it is possible.
Yeah, I think also for 4-point amplitude at 4 loop, you can choose 2 planar topology as master integrals. So just for convenience, it's use planar. It's simple. Yeah.
Okay, we did a question. So why couldn't one just start with the 4-loop BCJ answer and then just add? So I imagine that then you glue it together to the form factor, you get the 5-loop. Then you just have to add some more like compact terms to correct the ones that are not matching the cuts because of the.
I think what you are saying is kind of like the unitarity construction, right? So you have.
But I mean, you're taking literally the entire 4-loop piece, which you already match all the BCJ.
Yes, but it's just from these diagrams, you would consider this like a 4-loop 4-point, right? But this is only give you 1-channel information. You see the 5-loop results contains much more than 4-loop 4-point amplitudes. For example, it contains 3-loop 5. So if you can also do this channel. So this information would not contained in this one. So that's why if you just use 4-loop 4-point,
There's no need to do dimension cuts.
Right. That's a good question. So far the checks I have done is just for based on 4-dimensional cards.
And we don't expect any need for D-dimension.
I would agree with you. Yeah, it probably also works for. I think more concrete check would be based on use a D-dimensional check. I agree with that. But because
L dot L for 4-loop long
yes, yeah, because the numerator you see that increasing those high order of L loop momentum products.